So, let me just remind you what we were doing last time. So we've decided that a biharmonic stream function, psi, can be written in terms of these two complex potentials, f and g. Okay, so these are the analytic functions. And what I want to do now is to look at various types of isolated singularities of these f and g, and to see what they correspond to physically. So let's study isolated singularities of f and g. Aha, that's better. Okay, and the thing I left you with last time, on Friday I think, was to suppose that f of z, say, is this, has a logarithmic singularity of some strength mu at z naught. So z naught is some point. These are both just complex numbers, just constant mu and a z naught. Okay. And what we want to do is seek a solution with u and v logarithmically singular as you go towards the singularity. These are the velocity components. Okay. So we're letting f have a logarithm, and we want to find a corresponding flow where the velocity components are logarithmically singular. Okay. So to do that, let's recall that if you want to know what the complex velocity is in terms of f and g, then it's this. Okay. Remember I derived that, I think, on Friday or Tuesday last week. So this complex velocity vector is related to the f and g like that. Now, the first thing to notice is that f, of course, is not single-valued as you go around z naught. It's got a logarithmic branch. It's a logarithmic branch point there. And remember that the complex logarithm's got an infinite number of sheets, branches. But let's not forget that physically, the velocity field must be single-valued, because these are physical variables. So, note, u and v must be single-valued. Well, this is basically just so that they're physically sensible quantities. You can't have a flow which has multiple values of the velocity at the same point. And can you see that we've got some work to do then? Because we can't just assume that f is logarithmically singular like this without making sure that this particular combination of things, which is the u and the v, is single-valued. Okay? So we've got some work to do here. So let's see what we need to do. So first, let's just work out some things, because we need this and this. So if f is this, then F bar is, of course, the conjugate of everything. Log is a real function. The Schwartz conjugate of the log is the log. It's the same thing. And F prime is, of course, the derivative of this. So let's substitute. All I've done is substitute F bar of Z bar here and this here. And I haven't decided on G yet. G. Okay, so simply by assuming F has a logarithmic singularity at Z0, then this is what the velocity field is according to the formula for the velocity field in terms of F and G. And now we have to decide G clearly has to be chosen so that this quantity is single valued. Okay? Can anybody see what a good choice would be? You see, this is single valued, by the way. This is fine. It doesn't. If here's Z0, if I go round Z0, this just goes back to, this thing goes back to the same number, but this doesn't. So can you see what we have to put here in order to make this thing single valued? Okay. First of all, notice that it has to be an analytic function. We have to think of this is not single valued. So somehow, and this is, so somehow we have to use this freedom to make sure that this plus this is single valued as I go round Z0. And I'm constrained that this has to be an analytic function. Well, how about this? It's got to be an analytic function. That's a constant. And you know what? Let me add some other function. Call it g hat prime. And you'll see why in a second. Because then we've got this thing, look. Let's put this part together. And then I'll put this and this together. And now you can see why I did that and why that was a good choice. First of all, notice this is just an analytic function. It's just functions of z. There's no z bars, so it's okay. So this is perfectly acceptable. But look what I've managed to do here, look. I've made sure, look, that this is log of this. Suppose I take that out, that common factor, I've got log of complex conjugate plus log of its complex conjugate. Okay, so in fact this is this thing. It's the log of the modulus z minus z0, which is perfectly single valued, because it's just the distance away, and that certainly returns to the same value if it's the same distance away. So I've made sure that this thing is single valued. This is already single valued. But there's still a problem with this thing. There's a problem with it because I asked myself to make sure that the solution was logarithmically singular as z tended to z naught. So this is log of the distance. But notice that this blows up like 1 over the distance as I get close to z naught. Doesn't it? So that's too singular. So it's single valued, so that's good, but it's too singular. I want a logarithmic singularity, no higher order singularities. So can you see what I have to take for this extra piece of analytic function to kill this off? And bear in mind, this is only allowed to be a function of z. But this is a function of z and z bar. So again, I've got some thinking to do. I need to think of a function of z alone that will remove this singularity. You see, if this was just an arbitrary function of z and z bar, I would just subtract this bit off. Just get rid of the whole thing, I'll subtract it off. But I can't, it's got to be an analytic function, that constrains you. But what about this? Well, I clearly need to subtract off this. But what do I put in the top? I can't put z bars. But how about I subtract the value of this numerator when z is equal to z naught, which is just a constant. In other words, it's minus z naught bar. That's just a constant. So this whole thing is now an analytic function. Yes, you see, it's nice, isn't it? It's an analytic function, and look what we get now. We get minus mu bar. That's nice. But then we get plus mu bar and now this, look, as z goes to z naught, this vanishes and this has removed the singularity. Okay? And I've just got something logarithmically singular. So this is okay. So it is single valued and logarithmically singular. So, summary. Was it minus mu bar? See, if I put g hat prime to be this, then I've just put it into there, and so the whole thing was that. Everybody understand? What was interesting about this is you don't see this in ideal flow. In ideal flow, you just allow the complex potential to have particular singularities, but in Stokes flows, what I did here is I decided what kind of singularity f was going to have, but it forced me to have singularities of the g prime, in this case that look like this, in order that physical things were satisfied. In other words, that the velocity was appropriately singular and single valued. So what you have here now are pairs of singular behaviors that give you a particular singularity type. And let me tell you, I'll tell you what the people in low-Reynolds number call this singularity. They call this a Stoke'slet. This is the complex form of the Stoke'slet, or indeed, this is the fundamental singularity of Stoke'slet. you could call this, we'll see in a second, that if you like, this is the Green's function for Stokes flows. You'll see why in a second. Any questions? And by the way, I'll tell you a little story. I worked this out for myself a few years ago because I was thought to myself, what's a Stokelet in terms of F and G? Because Stokelets, people in low-Reynolds-number hydrodynamics talk about Stokelets all the time. But if you look in the textbooks, they're always written in terms of r theta coordinates. Okay? But this form you do not see in the textbooks. But what you can do is you can substitute this into the velocity field now, and you can show if you introduce r theta coordinates that you get what you can see in the textbooks. Let's just ask ourselves why it's the fundamental singularity. You remember, if I've got some z0, say, and I draw a curve around it, C, do you remember the formula I gave you for the force on the curve? Total viscous force on the curve. So you can imagine, for example, this could be the boundary of a body. The force on the curve, or rather, I think this was actually the force that the curve exerts on the fluid. Whichever, it's just a minus of the other thing. Do you remember what this was? I derived this for you, or at least it was an exercise. It was the change in 2IH as you go around C. Look this up, or it's in the notes that I'm going to email you if you're interested, where H was this thing. And if you remember, it was almost the same as the velocity field except for a change in sign. So it was this, the plus F. So it's almost the same as U plus IV. I've erased it now, but with a change in sign there. So let's work out what the force is due to this singularity. Okay, so it's the change in. We can take the 2I outside. H, which is F. Go around C, where C is some curve surrounding the fluid, surrounding the Z0. Okay, so let's just substitute this in. Well, F was mu log Z minus Z0. This was plus mu bar Z over Z minus Z0 bar. And G prime bar is that thing. Please make sure I do all the right conjugates. Okay, so I need to look at the change in this quantity as I go around the curve. Well, what about these two things, this and this? They're single value, they don't change. So this is basically the same as 2I, and notice, look, I can write these two terms as this. As I go around C. Can anybody see what this is going to be? Well, first of all, is there going to be a force on this curve? I would think so, because remember, over here, remember what U plus IV was? It was minus F of Z plus Z. Okay, this is I actually used the conjugate of this, but notice this is almost the same as H, except H has a plus. Now, I picked F and G so that this thing was single valued. But you can bet that it's very unlikely if this with the minus sign is single valued, you can bet that if I now change that to a plus sign, this isn't going to be single valued, and hence, there will be a force. Because the force is the change in this quantity as I go around C. And here it is. So the best way to think of this, to compute this, look, is to think of this in polar coordinates. Then the conjugate is r e to the minus I theta. So that if you think about this, this is 2I times mu. Well, let's just work out what the r's cancel, you get e to the 2I theta. So the log of this is 2I theta. And so the change in this is 2I times, how does theta change as you go round Z naught? Current by 2 pi. So there you go. What do you get? 8 minus 8 pi mu. Okay? Everybody see that? 2I just came from 2I. The mu just comes outside. Log of this thing is 2I theta, and theta changes by 2 pi if I go all the way around. So that's 2 pi. Okay. So you get 8 pi mu. So in other words, the force on the fluid due to this singularity, and by the way, it didn't matter what C was, as long as it was some curve going around Z naught, then this is the force on the fluid. Okay, so it's a point force on the fluid. Okay, so Stokes lit corresponds to a point force on this fluid with this strength, so it's proportional to the strength of the logarithmic singularity. Okay, so whatever the strength of the logarithm of f is, basically you multiply that by 8 pi, and you get or minus 8 pi, and you get the force on the fluid. Any questions there? By the way, there's while I think about this, there's some Japanese researchers who use a numerical method called what's it called? Charge simulation for irrotational flows or electrostatic flows, where that you basically take an object and you replace it by a distribution of fundamental singularities. If you wanted to do the same thing for Stokes flow, you would be superposing singularities like this inside the body. Okay? So charge simulation method for Stokes flow would be built on these fundamental solutions. Okay, so they're more complicated for the Stokes flow than the harmonic problems. Let's do another singularity. Well, we tried, this is a different one now. Well, we looked at f being a logarithm. The derivative of a logarithm is a simple pole. So let's try f having a simple pole. So we'll let it look like this and seek solution with u and v going like 1 over. Okay, so u minus iv, remember, was this. It's not this, it's u minus iv, which is why I've conjugated everything. So, over here, let me just write what the conjugate is. It's lambda bar over z minus z naught bar. And the derivative is, of course, minus lambda over z minus z naught squared. So let's substitute those things. This is the velocity field associated with that. We haven't picked g yet, g prime. Now in this case, we don't have to worry about single-valuedness because f was itself single-valued and its derivative is single-valued. So this is all single-valued. But I do want to enforce this, that it only goes like 1 over distance as I get close to the singularity. And this thing, look, because of this derivative, is more singular than that. Does everybody see? It's the same problem as before. This looks like 1 over distance. This looks like 1 over distance squared. I don't want that. So somehow I have to fix it with the g prime. Or at least I have to get rid of one of those orders of magnitude with the g prime. So can anybody see? Remember, I need it to be analytic. And I've got that z bar there again. But I can do the same thing as before. So now I let me let this be lambda z naught bar, which is the value of this at this, divided by z minus z naught squared, which is an analytic function. So that's acceptable. And you can see that what I get is everybody see? This is just analytic, because that's just a constant, and this is analytic. And you can see what happens, look, as I get close to z naught, this vanishes like r, this vanishes like r squared, where r is distance. So this whole thing vanishes like 1 over r, as does this. So everything's fine. Okay, so over here, let me conclude with this. So if I have f having a simple pole, then I need g prime to have a second order pole with this strength. So if lambda has, if this f has a simple pole of strength lambda, this has to have a double pole with strength lambda z naught bar. Okay? And we have a name for this one too. That was a Stokelet. This one's what we call a stresslet. That's the name of a singularity, when f and g prime have this particular combination. What force does a stresslet exert on the flow? Do all this again. I do this again. All of this is still the same. But when I come to here, look, F and G prime and F prime for a stresslet, they're all single value. There's no logarithms anywhere. So there's no change on anything as I go around C, and so there's no net force on the fluid. Okay. So if I repeat all of this, the stresslet does not exert any force on the fluid. So since F prime and G prime are all single valued as Z encircles, well, traverses a circuit around Z naught, a stresslet exerts no force. Let's do one more, shall we? What's the next thing? I had F as a logarithm. That's a Stokelet. I had F as a simple pole. That's a stresslet. Let me have F as a second order pole. Then F bar. We can do this easily now. We understand what's happening. Okay, and U minus IV is make sure I get this right because I'm doing it quickly. And the point is here we want to seek solution with UV going like order 1 over Z minus Z naught squared as you get close to the singularity. And you can clearly see that this is more singular than that. So I have to pick G prime to cancel out one of those singularities. Okay? So you can see what I have to pick. If I pick this to be 2 plus 2 lambda Z naught bar all over Z minus Z naught cubed. Just as before. Okay? So if everybody see the pattern here? We'll talk about the name of this in a second. This was a Stokelet. when you take, if you think about the next order down for F, this is a stresslet, or some people call this or a force dipole. Okay? Or a force dipole. So stresslet and force dipole, different people use different words. So this one's called a force quadrupole. And you can see if I carried on taking derivatives, I'd get higher order force multipoles. Questions? All right, something else though. How about the following thing? In this case, so far, I've set singularities of F, and I've noticed that G prime has to have certain singularities as well to match the ones in F so that everything's single valued or nicely singular. But how about the possibility also of letting F be analytic? No singularities. But G has singularities. How about that? Did you remember? We're biharmonic. We've got F and G. So we can play around. So, but G, or let's call it G prime, because that's what appears in the velocity field, can have its own singularities, even if F is non-singular. Well, let's just check the velocity field, look. This was G, not G prime. Let's put G there, it doesn't matter. Let's put G having a logarithmic singularity, and F 0. That's analytic, isn't it? Then the velocity field, look, these both vanish. G prime is just that. Does anybody recognize that? Look, if F disappears, I'm back to the case of ideal flow. So all of the singularities of G are exactly the same as the ideal flow singularities. And for ideal flow, if W, I called it W, was logarithmically singular with a purely imaginary strength, I called it a point vortex. Remember? I'm doing the same thing again now, but it's Stokes flow. I'm going to call this a Rotlet singularity. It's the same flow though. So this corresponds to and G prime this is a Rotlet. Suppose it was purely real. Suppose the coefficient was purely real. And f is 0. Or just some analytic function z naught. Does anybody know what they're called? In ideal flow, this is an example of a point source or sink of strength m over 2 pi m. Point source or sink. Let's do example 3. Suppose G looks like this. So I'm not letting F have any singularities, but I'm looking at the higher order singularities of G now. This is the normal dipole. So you can think of two sources, or a source and a sink of opposite strength, or a vortex of one sign coming together with another sign. So this is just an irrotational dipole, or often you'll see these phrases, a source dipole. Notice I've used the word source dipole here, which is distinct from a force dipole, which I've erased, but it was when F has a simple pole. You understand? You see, look, does everyone understand the difference? So this is a source dipole when F is analytic, but G has a simple pole. A force dipole corresponds to F having a simple pole, and G prime, of course, having to have this to go along with it. Okay? I just derived this earlier. This is the stresslet. There. That's a force. That's also known as a force dipole. This is a source dipole. F is analytic, but G has a simple pole. And I can go on. If G looks like a square and F is 0, we call this a source quadrupole. Etc. Yeah, source octupole and higher order multipole. Everyone understand? Audrey?
Yeah, also I was just but can't you also pick F and G so in these examples you've chosen F and G so that you're choosing a logarithm saying that you want the velocity field to be you're choosing an order of singularity.
That's right.
The same order of singularity.
Yes.
Can't we say, well, we're going to choose F and G to have one kind of singularity, but we want the velocity field to have a different kind?
True. But then they're a superposition of these different types. You see, what this is like a catalogue of the basic singularities, and then more complicated singularities are a superposition of these things. You see? So what this does is it allows us a unique way to describe what the singularities are. So for example, we'll see, in fact, we'll answer this question in a second, because what we're going to do now is we're going to take one of these singularities and put it near a wall. And then we'll get an image singularity, and we'll see what type it is, and we'll see how to describe it. Okay? So that will answer your question, I think. Okay? So yeah, you're right, you see. I can have a kind of log singularity with some higher order singularities in it, and then you say, oh, well, there's a Stokeslet there, but it could be a superposition of a Stokeslet with some higher order multipoles. Yes.
I'll give us a
That will give us a superposition of a Stokelet and a Rotlet. Stokelet of strength mu, Rotlet of strength mu bar. This is, you see, you can decide what the strengths are. You'll see. What we'll do now is we'll do what I was planning to do next, which is a case of near a wall. Remember what I showed you at the end of the last lecture about the swimmers near the wall. See, what we're aiming for by the end of today is to understand a model of swimming near a wall. Okay? To do that, we need to understand the basic singularities. Yep. Each case is.
Can we picture in ideal fluids
The streamlines.
F1 the complicate. In ideal fluids, one analytic function, but in Stokes fluids, two analytic.
That's right.
Can we picture
Pictures of the flows.
So we I don't understand source or
Okay.
named.
Yeah, I understand. Yes.
Why named?
Yes. So for example, we all know, don't we, this one. No, this one. If you want to, by the way, with all of the singularities I've described here, you can certainly go away now and plot for yourselves the streamlines. Because remember, psi is the imaginary part of z bar f plus g. So if you wanted to go to MATLAB or something and put in the f and g for each of these singularities and just plot contours of psi, it will show you the streamlines. That's the easiest way to do it. You could actually try to work them out yourselves. Okay? Usually the best thing is to move to polar coordinates and then try to prove. It's not actually very easy. This one we know is purely circles. Because it's the point vortex or the Rotlet. Right? This one is the top one there. Source or sink, the streamlines look like that. If you're ejecting fluid at some rate proportional to m. This one is a dipole. Okay? And the streamlines look like this. If mu is real, they look like this. Okay? It's a dipole. Source dipole. Force dipole, do it as an exercise. Let me just tell you what a Stokelet looks like. A Stokelet is literally like a force. By the way, if mu is purely real, it will literally look like a force aligned with the x-axis. Okay? And what it does is it produces streamlines that look like this. You'll see. It basically imagine you just forcing fluid. What you'll see is a kind of recirculation zone, because actually, if you drag a cylinder through a fluid, then it looks like a Stokelet. Okay. I haven't drawn all the streamlines because you have to. Some of them are quite complicated for the force singularities. So you should draw. So for example, try a stresslet. You can write down what the size for a stresslet for lambda real, say, and you can sketch the streamlines for yourself.
In adaptation by analytic function,
Uh-huh.
similarly ideal fluid.
These are similar to the ideal fluid when F is 0. But when F is not 0, it's more complicated. Yeah. You've probably seen these all before. Everything here is what you would have seen if you did ideal fluid mechanics. Except I don't call it a point vortex anymore because it's kinematically a vortical flow. The streamlines look the same, but it's very viscous fluid being dragged round. And we call it a rottlet. Okay. But all of these force multipoles are very different to what you would have seen before. You've got F and G. It's a nice exercise to just plot locally what all the streamlines look like for the force multipoles. Okay, you know what? I'm just going to pose the problem, then we'll take a 5-minute break and leave you to think about it. Let's do a rottlet near a wall. Okay, so there's the rottlet, look. In fact, let's keep that. This is a nice example, because remember, if this was ideal flow, and I put a point vortex near a wall, we already know what that does. I did it last week. It travels at uniform speed, remember? And I found that the image was a point vortex of the opposite sign that sat beneath. Compare that with what we're going to see now, because we're going to put this rottlet near a wall. What's the difference? What's the difference between those two problems? Here we go. Here's the wall. And there's Z0. And there's a little rottlet. Actually, let's make it actually look like a point vortex. Okay? So this is, sorry. What I'm saying here is that G looks locally, let's be more precise. It looks locally like this plus something else. Okay, so it looks like, oh, sorry, this is G prime. You see, I always oscillate between G and G prime because G only appears in the stream function, and normally you work with velocities, where G prime only appears. So G prime is going to look like this. Okay? What have we got to do then? Whenever you solve a Stokes flow problem, you've got to find F and G. That's the whole point. All I know is that G prime has a simple pole here, plus something else that's analytic in the upper half plane. I've got to find this. And F is not even singular at Z0, and it's analytic in the upper half plane. So I need to find F and G hat prime that are analytic in the upper half plane. But what's the boundary condition? This is a solid wall. Well, remember, if this was a point vortex problem in ideal flow, we just insist that there's no flow through the wall. But it's a viscous fluid now, which means we've also got to, it's an impermeable wall, so there's still no flow through it, but it's also no slip. So we need to find f of z and g hat prime of z analytic in upper half plane such that u minus iv equals 0 on the wall. That's our problem. Okay. So let me just stop for 5 minutes while you think about that. And we'll try when I get back. Okay, let's see what we can do with this. We need to find g hat, prime, and f. Okay, so that the no slip condition on the wall is satisfied. So let's recall, we know this now, we've seen it lots of times, that this is minus f of z bar plus z bar f prime of z plus g prime of z. Right? And the whole point is, this is equal to 0 on the wall. That's the boundary condition, where z bar is equal to z. Hence, look at this. Look, on the wall then, this is the conjugate of f of z, which is basically f bar of z bar, but I'm on the wall, so z bar is equal to z. So it's f bar of z. And that's just z. And that's just f prime. Okay? Now, that's true on the wall, but of course now what I have here is a relationship between three analytic functions. G prime, f prime, and f bar, which is the Schwartz conjugate of f. Now, this is true everywhere on the real axis. It's a relation between analytic functions, and therefore we can continue this off the real axis by analytic continuation, it's called. And this basically gives a relationship between g prime and f and its conjugate everywhere. That's the beautiful power of analytic continuation. Okay? So i.e. at least everywhere it can be analytically continued. Okay? So let's just try something. Well, remember, F, the F that I'm looking for has got to be analytic in the upper half plane. So I'm not going to try anything. I'm going to try some guesses here. I'm not going to try anything that isn't analytic in the upper half plane, because I need F to be analytic there. But you know what? Z0 is in the upper half plane, and my intuition for the method of images is that at least when F is 0, so the irrotational flow, there's a singularity here. So let's just see what happens if I put a singularity, say a simple pole, at Z0 bar, where I haven't decided what lambda is yet. Lambda is some complex constant. Notice this is analytic. By the way, is it okay if I say upper analytic? That just means analytic in the upper half. It's shorter. See? Because that has a singularity here. So this is acceptable. Okay? So what I've done here is I've guessed a possible F, which is admissible, and now this tells me what G is, including off the axis. In other words, up there. So let's see if a form of this form will give us what we need. So hence, well, let's just do the calculations over here. I'm going to need, okay, let's just do this. What's F bar of Z? Everybody watch. That's what I need, look. Look, I need two things. I need F prime. Let's do F prime first. F prime is easy. It's easy. What about F bar of Z? Well, you remember how I told you to work out conjugates, Schwartz conjugates. You look at the function, and every time you see a complex constant, you conjugate it, but you leave Z alone. So F bar of Z, look, the top is a complex conjugate. I take the conjugate at the top, and I leave Z alone, and I take the conjugate of the bottom. See? It was Z0 bar, and I conjugate that, I get Z0. It was lambda, I conjugate that, I get lambda bar. That's the Schwartz conjugate of F. So if I now substitute these into that, okay, this minus sign cancels with that minus sign to give me a plus. What do we think? I just took a guess. But if I guessed that F, this is what G has to be if the no-slip boundary condition holds. Is this is okay. This is acceptable because F is upper analytic, but G hat prime, I need that to be upper analytic, and I also need G to have this singularity. Can I make that happen? Remember, I haven't set what lambda is yet. But this is what G prime has to be if F is this, for some lambda, and if the no-slip condition is going to hold. So can you see, look, that this is perfect? Because if I pick lambda bar correctly, I can make sure that first of all, there's a simple pole at Z0, which is exactly what I'm looking for. Provided I pick lambda bar to be minus I gamma over 2 pi. And do I care about this thing? Well, I do. I would need to see, this is my potential G hat prime. All I need to check is it analytic in the upper half plane? But it is, look, because it's singular at Z0 bar, which is downstairs. Okay, so pick Everyone see that? Oh, let me just do some. I'm just going to do some trivial things here. To answer Roger's question. It's just algebra. Okay, does everybody see what I did? This was my answer. This was my answer for G prime. Look what I did. First of all, I saw the Z there. So I made it, instead of Z, I subtracted Z0 and added Z0. Then look what I did. This is I kept the same. Then I put this one, look, everybody watch. I took this one and I put it there. And then I left this one, which was supposed to be these two, look. But I subtracted Z0 bar and I added Z0 bar. It's just algebra. But this is an identity. And then this is the final answer, and notice that that is that. This is this. And then, look, I've cancelled one of those to give me this one. And then this is a constant. This is, everybody see? It's just algebra. So now, the reason I did that is because I want to show Rodri the answer to his question. What type of singularities do I have at the image point now? And the reason I did all of those algebraic manipulations is because I've put them into a form we can recognize, according to the scheme I introduced earlier. So, this, of course, is the physical rotlet. It's the only singularity. Oh, sorry, there should be a bar over that. This is the only singularity in the upper half plane. That's the Rotlet, with lambda this. Now let's look at F. F has a simple pole at Z0 bar, which is down here. What do we call singularities where F has a simple pole? Remember? F was a log, it's a Stokelet. F was a simple pole, it was a stresslet. But remember, when F has a simple pole of strength lambda, G prime has to have a second order pole of strength lambda times the conjugate of the position of the singularity. Just look at my cataloguing. So look, F has a simple pole at Z0 bar, but look, here is G prime has a second order pole there with the same lambda and the conjugate of the position of the singularity. You understand? So this combination is what I called a stresslet. So it's an image stresslet. What's this? Well, I've got the stresslet together, and now there's no more singularities of F left, because that's the stresslet. But now I've got a simple pole of G prime, which is a logarithmic singularity of G, and a second pole of G prime, which is a simple pole of G. So this is what we call a point vortex. This is what we call a Rotlet. Depends on whether this is purely imaginary or it doesn't matter. So this is a Rotlet stroke source sink. And this one is a source dipole. All of these are images. By the way, we could have yes, we could have anticipated this one, couldn't we? Because this and this one are the ones that give you no, make it a streamline. This is one you'd expect if it was just a point vortex and you weren't imposing no slip. Okay? This is the point vortex solution. But what's interesting about Stokes, though, is you get two more image singularities. You get an image stresslet and an image source dipole. Okay? So it's hard to explain, but if you put a Rotlet near a wall and it's a no-slip surface, and down here you get an image Rotlet plus a stresslet and an image source dipole. All of the strengths that you see on the top of these numerators here, and they have to be carefully chosen. Okay? So the message is, in my view, that it's method of images. You can still interpret this as an image system, but it's not at all clear how you would have guessed what it is before you started. But notice that it all just comes from this analytic continuation of the no-slip condition. that answer your question?
Yeah.
Yeah. You see, so each one of these singularities falls in one of the classes I introduced earlier, even though, you see, these singularities both sit at the same place as the stresslet, right? But I define the stresslet to be this particular combination of things. By the way, that's just my convention. Other people do different things. For example, some people stick bits of this into what they define to be a stresslet. Okay. Is everybody happy with singularities in Stokes flow now? Maybe not. I think you've seen the idea. So let's get on to swimmers. So you remember I showed you yesterday, Friday, that the slides, I'll send you the slides, where people were doing all kinds of things with numerical experiments with you know, models of sperm with ellipsoidal heads and helical tails, and they were solving these numerically. And what you saw is, and then of course remember the rods with these actuated spheres connected by rods. Completely different swimmers, but one of the things that we noticed was that there was a phenomenon of oscillating to a steadily translating state near a wall. Both this and this were seen to do that. And there were also these nonlinear periodic orbits. Do you remember these? So what happened was you would get close to the wall, you would reorient, and then you'd move away from the wall. Then you'd go back and you'd repeat the sequence. So we had a steadily translating state. And these are what I call nonlinear periodic orbits. So these are just some typical dynamics that you could see were common to these low-Reynolds-number swimmers that were completely different. Rods, with spheres and rods, and then sperm, models of sperm. And so, about 5 years ago, Yuzar Orr, who was doing these calculations, came to me and asked me if I had any thoughts. And do you know what I said to him? I remember my exact words. I said, what does a two-dimensional stresslet do near a wall? And he didn't know the answer. He couldn't tell me. But here's the reason I asked what a two-dimensional stresslet does near a wall. When people were looking at the motion of these model swimmers, they were actuating. For example, they would have this coil spinning around at some angular velocity, or they would have these oscillating, turning around at some angular velocity. But basically, the whole thing exerted no net force on the fluid and no net torque. And those two constraints led to the thing moving like this. Okay? So the point is that far away, if you think about whatever this swimmer is doing as a singularity of Stokes flow, it can't be a Stokelet because it's no net force. Okay, so it was a natural question for me to ask, what does a two-dimensional stresslet do? A two-dimensional stresslet do near a wall? Okay. And then I had a better idea. He didn't know the answer, but then I had the following idea. Given that it doesn't seem to matter the precise details of the swimmer, but we're seeing the same dynamics, let's make up our own swimmer. That's as simple as possible, and see if we observe the same thing. So what I did was I picked a circular swimmer. So this is our model swimmer. So let's for now say it's a unit disk. And what I'm going to do is I'm going to impose, let's have no changes in shape, because that's difficult. But we need to actuate it. It needs to create some flow around it. So let's impose a tangential slip. And of the following form. Right? Yeah, here. Now, one thing I did was I put an axis in here. So you should think of this as a head-tail axis. Okay, it's just the diameter, which is marked in the disk. The reason I had to do that is because the condition that there's no net torque on these swimmers means that they reorient. And so you want to keep track of how it's reorienting. And if it's just a circular disk with no distinguished direction marked on it, you won't see it rotate easily. So we're going to have a head-tail axis on here. It's just drawn on the thing, and it will be at angle theta to the x-axis. And then what we're going to do is, if this is a point with angle phi, we're going to impose this slip. Twos are there just for convenience, you'll see. U and V are just real constants. Okay? Maybe I'll draw a better picture of it. Okay, so here's my swimmer. It's a unit disk, and it's got a head-tail axis, some distinguished orientation, and then relative to this, axis. Maybe I should do this because I want to explain. I'm just trying to give you an image of the imposed slip. And this is the boundary. Yeah, the red and blue arrows are just to denote the two components of the slip, U and V. Okay, so look, notice that there's a 1 here and a 2 here. So you see, suppose U and V are positive. When this angle here is between 0 and pi, this whole thing's positive. Okay? Which is why I've drawn this big yellow. So in other words, This is where theta is between 0 and pi. It's got a big positive arrow, and then it vanishes here. And then it becomes negative, which means the flow's in the opposite direction as I go around the rest of it. Okay? And then notice there's a 2 here, which means that as I go around this portion of theta minus phi, it's one direction, then it changes direction, then it changes direction again, and then it changes direction again. Okay? So I'm just trying to, and this is tangential slip. Okay? So this is the idea we had. The whole point is we're trying to do something on the surface. By the way, you should think of this slip as being produced by cilia, little cilia hairs on the boundaries of the swimmer causing a local motion. Okay? So let's find F and G. In other words, I'm going to solve for the flow, the Stokes flow around that swimmer. There's no walls. It's just a swimmer in free space. I'm going to solve for the flow around it, assuming there's no net force at all. So let's imagine it's centered at the origin. So this is the origin. What's the complex form of the unit tangent? Well, remember, if this is some point on the swimmer, this is z, and this is unit length. Okay, so this is z. So the normal is z, complex normal is z. What's this vector? You multiply by I to rotate it by 90 degrees. Okay. So the normal is z, unit normal is z, because we're on the unit disk. This is 1. And then, so the tangent is IZ. The complex unit tangent is IZ. Okay? So we need to find F and G such that let me check I'm doing the right one. I'm going to do U plus. So look what I'm doing. The velocity on the boundary is the following. This is the tangent vector. And I'm imposing this real valued slip in the tangent direction. But I'm also going to enforce the fact that the swimmer does not experience a net force or torque. And that means that it will have to translate at some complex speed us that I've got to find and rotate with some angular velocity omega s that I also have to find. Okay? And the values of this and this will be determined by the constraint that there's no net force and no net torque. Does everybody understand? This is very important because this is the essence of low-Reynolds-number swimming. So this is the essence of a huge branch of science. Let me put it to you differently. Suppose I gave you a US and I gave you an omega s. And I've given you this. That would mean that the boundary velocity would be this translation plus some rotation and some boundary slip. Now, if I told you this, I told you this, and I told you this, and I decided them at random, it would imply, in general, a net force and a net torque on the swimmer in order for it to move with that velocity. Because you're basically dragging some, so what you're doing is you're dragging and rotating some object with some extra slip on the thing. And in order to do that, you would need a net force and a net torque. But that's not the problem I'm considering. I'm saying, let me suppose that there's not allowed to be a net force or torque on this thing. I will insist, however, that the slip is of this form. But then, the values of this and this will come out. See? They will be dictated by the condition that there's no net force or net torque. Everyone understand? I'll say it again because it's so important. If I set that to be 1 and that to be 1, there would be a net force and net torque that I could compute. But I'm saying there's no net force and there's no net torque. So US and omega s have to be something in order to make sure that's true. So they're parts of the solution to my problem. And the only reason I'm doing that is because that's the physical problem for low-Reynolds-number swimmers. Okay. So let's see if we can solve this Stokes problem. All right, so we've got the unit disk here, and we need to find f and g that are analytic outside this unit disk, satisfying this boundary condition. This, by the way, is true on mod z is equal to 1. That's the boundary of the swimmer. Well, I'll tell you what, let's just do some preliminaries first. So here's a little exercise for you. I don't really want to do this. It's just calculations. If I let z be e to the I theta, then 2u sine phi minus theta is minus I c bar z minus c over z, where c is defined to be u e to the I theta. It's just algebra. I'm just trying to write this in complex form, where I'm letting z be some coordinate on the circle. Okay, this is just calculations. And hence that, I don't need to do this. what I need. Let me just explain what I did. This is the boundary condition. I need to find f and g, though. I always need to find f and g. I know what u plus iv is in terms of f and g. That's just this. I also know that I need that velocity to be this. I've just rewritten those. And then I've used these facts together with the fact that the tangent is iz, and that's why the i's have disappeared, because I've got an I there and a minus I here. So you don't see i's anymore. And this comes from the z outside, and this is from the sine, the two sines. Everyone happy? So this is true on the boundary. Okay. And these are to be determined as well. C and D are given. You give me capital U, you give me capital V, and the angle is a geometrical parameter. So I have to find f and g prime now, analytic outside the disk with no net force or torque on the swimmer. And they have to satisfy this boundary condition. That's the mathematical problem. Okay. Now, how would you do that? I need to find this f and g. They're analytic outside the disk, the unit disk. And there's no net force or torque on it. Well, how about this? What do you know about if you've got the inside of a unit disk and you've got a function that's analytic inside the unit disk? What's one way to represent such a function? Function analytic in the unit disk. Everybody learns about it in complex analysis. Taylor series. It's one way to represent a function analytic in the disk. If you've got a function analytic outside the disk, by the way, Taylor series is just a series of positive powers of z. Suppose I'm outside the disk. How would you represent a function that's analytic outside the disk, including infinity? Well, you use a Laurent series, which is a powers of purely negative powers of z, because you want it to be analytic at infinity, so you don't include any positive powers. So let's and by the way, I'm not going to include any logarithms at infinity either. Why? For f and g. Because I don't want any forces. So, at worst, I'm going to have negative powers of z. So let's do it like this. And these coefficients I need to find. Now, I'm going to sneak something in here. you noticed something strange about my G prime expression? I've missed out the 1 over z term. And I did that because if you look back at your notes, I didn't derive it for you, but I told you to do it as an exercise, and this is the talk about the origin. In other words, if I wanted to talk about the origin here, you'd find that it would be 2 times the real part of the contour integral around the thing of G prime. Okay? And I think you can see, right, that the only way you're going to get a non-zero torque is if you have a 1 over z term in the G prime. Okay? So I've omitted it because if I kept it there, I would have a non-zero torque. Okay? So, and we have omitted the 1 over z term in G prime to ensure no net torque. By the way, I could have also included constants here, but it turns out the constants don't matter. You can always remember, actually you suggested are they unique, and they're only unique up to adding constant. Remember that you could add a constant to f and take it away with G prime, and the velocity field would be the same. So the constants don't matter here. I need a 1 over z term for f, but I can't have a 1 over z, so there's no 1 over z term here because it would imply a torque. Okay? Everybody knows this, right? That's the basis of the residue theorem. So the 1 over z term is G prime is precisely the one you want to be 0 if you want 0 net torque. Okay, so now you see what I have to do. I substitute these into here, and I equate coefficients. Let me just write it out, and you'll be able to see how it works. So f prime is that. So f prime bar of z notice that I'm on the unit circle, where z bar is 1 over z. So look, this is f prime. I just took the derivative of that. But here I'm going to need f prime bar. So it would have been minus f1 bar over z bar. But z bar is 1 over z. So it gives me minus f1 bar z. Similarly, minus f2 bar z squared. And similarly, g prime z bar so let's substitute want to see what I'm doing here? Which is taking those f and g prime. I worked out the derivative. I've worked out these two things on the circle, where z bar is 1 over z. So that the whole of the left-hand side will be some Laurent series in z, and the right-hand side is clearly already a Laurent series. So I'm equating the powers of two Laurent series. Okay? And let me just tell you what you get. Powers of the constant powers give you this. The order 1 over z term gives you this. The order z term gives you this. Then order 1 over z to the n I'm just running these down so you can check them for yourself. Just equating coefficients. Okay, good place to stop for a 5-minute break. I've got a question for you. 2 questions. First of all, this swimmer is just a swimmer in free space. There's no walls. And it's actuated with this treadmilling action. Question is, what speed does it move at? And also, the next question is, what kind of singularity does it look like far away? So it's a circular object with a treadmilling action, but far away, it's just going to look like some superposition of some Stokes flow singularities. We went through them all earlier today. So there's 2 questions. What speed does it move at? How does it rotate? And what are its singularities far away? What does it look like as a singularity far away?
Okay, so have a think about that for 5 minutes. The answer's on the board.
Just write down the answers for you. Notice that the only non-zero coefficient of f is the first one. So the first question was, what speed does this swimmer swim at? Well, here it is. C, remember, was given as this. And I told you, these are what they have to be in order for there to be no net force and net torque. So the speed of the swimmer is C. It moves with speed U at angle theta to the axis. It doesn't rotate. So this swimmer, with this particular treadmilling action, doesn't rotate. But it moves along the axis of its orientation with speed u. And let's answer the question, what type of singularity does it look like far away? Well, it's quite nice. It's just a finite superposition of singularities. We've got a simple pole of F at the origin. What do we call simple poles of F? What type of singularities? Let's look back at our notes. Simple pole of F. We called those stresslets. So this is a stresslet of strength mu is equal to v e to the 2I theta at z is equal to 0. What's this? Well, actually, let's do with this one first. Well, by the way, remember, whenever F has a simple pole, G prime also has a double pole, but its strength is mu times the complex conjugate of the position of the singularity. Now, the position of the singularity is the origin here. So we don't get any contribution to G prime from this bit, from this. So this is the stresslet, but there's no contribution from G prime. Because Z naught bar is 0 in this case. Z naught is 0. Now, so G prime has its own singularities at Z equals naught. This one is a source dipole, and this one is a source quadrupole. Okay? So there you have it. This swimmer that I made up moves at speed c, which is u e to the I theta. It doesn't rotate. And far away, it looks like a stresslet with a superposed source dipole and a superposed source quadrupole, where if the stresslet strength is mu, you can see that the quadrupole strength is related to mu, and the dipole strength is related to the speed. Okay? Interesting, eh? Let me tell you why I made up my own swimmer. I made up my own swimmer because when you study Stokes flows, as I've shown you, there's lots of different singularity types. So which one do you pick? I didn't know which one to pick. When Yiza asked me the question, do I have any ideas? I asked him, what does a stresslet do near a wall? But then I realized that I could have asked, it could be a stresslet plus all kinds of other singularities. Which one do I pick? Which one do I want to study? So to answer that question, I did this piece of analysis, I made up my own treadmilling swimmer. And now I have an answer. It's a stresslet plus a source dipole and a source quadrupole with these particular combination of strengths. So it was a way for me to decide on a choice of singularities. Okay? But based on an actual physical swimmer that's got little treadmilling on its surface. Okay? Do people understand? Right. What do you think Yiza and I did next? At the moment, I've just made up my own little circular swimmer. Simple as I could think of. And I've decided, and I noticed by studying it in just in free space, no walls, that it looks like this point singularities, 3 of them superposed. But remember, we were interested in what swimmers do near walls. Well, we had 2 choices. Option 1 is the following thing. Now, which one should I do? There's two options. Which one should I do first? I'm going to do it in the order of history. What we did is we decided, look, suppose now there's a wall, and I want to know what this little treadmiller does if it's placed near the wall. When we first did this, I didn't want to put a little circular treadmiller near the wall. It's too complicated. And the fluid domain is doubly connected. So I didn't want to do that. What do you think I did instead? Especially given that lecture between 4 and 5. I know that my swimmer, if I look at it far away, is a superposition of a stresslet, dipole, and a quadrupole. Point singularities. So one option is to say, I wonder what that point singularity combination does if you put it near a wall. Okay? The assumption being that, provided the swimmer doesn't get too close, here's the wall, provided the swimmer doesn't get too close to the wall, as far as the wall's concerned, it will look like those 3 singularities put together. If it gets too close to the wall, that will be a bad approximation. But far away, you could ask yourself what a point stresslet plus a point dipole quadrupole combination does near a wall. The point being that it's a point singularity. Does everyone understand the idea behind that? It's almost like, it's like a far field approximation. Your swimmers over there, it's making some flow actuate. But far away, all you see is these 3 singularities superposed. So let's ask what that does near a wall. And then we can use all the techniques we've learned in this lecture so far to solve this problem. Okay, and that's what we did. But let me just tell you what else you could do. You could put the actual treadmiller near a wall. Okay, so here it is, with this little axis and its treadmilling action. And what I didn't realize at the time, but I'm going to tell you on Friday, is that you can solve this analytically too, using some remarkable results based on the reciprocal theorem. And I'm going to show you that on Friday, because when I first did this, I didn't realize you could do that. I worked it out a couple of years later. This is a much more difficult problem. So put the actual treadmiller. Near the wall. I didn't do that at first because I thought it was too difficult. Can you see how difficult this is? See, you've got to solve for f and g now in this doubly connected region with no slip on here and the strange slip condition that I've just analyzed on here. So that's a difficult problem. But in fact, it can be done. So we're going to do this one. Because we can all do that now. So here we go, look. All we have to do is, if we now put it at a general position, so in other words, not here, it would be this. Remember, you need this to go with the stresslet. This is the stresslet. And I'm also going to do one more thing. I'm going to just explain what I did here, because I've skipped a couple of things. First of all, I've set U, capital U, to be 0. Which means C is 0. Which means that this swimmer won't move at all if there's no walls. Right? Look, this was the speed of the swimmer if there were no walls, and it was given by C. But if I set U to be 0, it won't move at all. And do you know why I did that? I did that because I wanted to see how the wall makes it move. By the way, mu here is this. Might even be, no, it's this. So in other words, I've got rid of this term. I just set u is equal to 0. And the other thing I've done is I've allowed it to possibly be of different radius than 1. Okay, so remember, everything I did there for simplicity was unit radius. But if I change the radius, it turns out I have a scaling factor here. Okay? Actually, there's an epsilon here, and this becomes an epsilon cubed, but I can absorb one of them into the mu. All you need to know is that we have a stresslet of strength mu with a source quadrupole of strength 2 mu epsilon squared, where epsilon is up to me. So it's a stresslet, strength mu, and a source quadrupole of strength. Well, it depends whether you want to do g or g prime, but let's just call it 2 mu epsilon squared. Okay. I know there's a lot to absorb here. All I'm doing is I'm just restricting to a special swimmer that doesn't move on its own. And I've just rescaled it so it can have different radius. That's why the epsilon comes in. Epsilon was 1 earlier, but now I've let it be arbitrary. And everything else is the same. And it's at z0, not the origin. That's all I've done. Okay, so let's see if we can test ourselves on what we did earlier. Let's put a stresslet near a wall, because that's what we've got. Okay. So we want okay, so this is the stress limit. Well, let's recall what we did earlier. Recall that U minus IV is minus F Z bar plus Z bar F prime. You're getting used to this now, I'm sure. And this is 0 on Z bar is Z. So again, we have that analytic continuation result. This is as before. Okay, we did all this earlier with the rotlet. We were looking for a rotlet earlier, but now we're doing the stresslet. So my advice is to just try a few things. So let's try. We know we want F to have a simple pole. So let's try F having mu over Z minus Z naught. That's all. Then F bar of Z is, everybody watch, remember it's the conjugate function, so you conjugate mu, you leave Z alone, and you conjugate that. And then we need F prime, which is minus mu over Z minus Z naught squared. So let's substitute. Remember what I've done? I've tried, I've guessed. This is a guess. If this is true, then this is true, and this is true. And if I want no slip on the wall, G prime is given by this, which is this. Now, I want this. Have I got it? Well, look, I want a second order pole at Z naught with strength mu Z naught bar. I don't care about this. That's a singularity in the lower half plane. Aha! G prime has a second order pole at Z naught. What's its strength? It's the value of this at Z naught, which is mu Z naught. Is that equal to mu Z naught bar? No. No. So, this, not enough. Good try, not enough. Any other ideas? Let me try something else. Go over here and try something. Let me try, what do I want to try now? Okay. Look what I've done. I know that I can put F looking like this, and it will give me the right type of singularity of G prime, but it's the wrong strength. And remember, by linearity, I can always keep that there. But I need something else to fix it. So what I'm going to try now is I won't let F have a singularity Z0, but I'll put a double pole at the image. So this is analytic in the upper half plane. Okay, let's work out the other things we need. We need F bar Z. Remember, everybody, watch me. That means every time I see a constant, I conjugate it. I leave Z alone. And then I conjugate that one. And we need F prime. So let's substitute into that. Let's look at the answer. Here's what I've done. If F looks like this, which is fine because it's upper analytic, then F bar looks like that and F prime looks like that. And G prime, if the no slip condition is to hold, looks like this. Look at this. This is the important thing. I've got a second order pole of strength lambda bar, and I haven't said anything about lambda bar yet. But it's a second order pole at Z0. And then this one's upper analytic, so I don't care. So what do you think I should do? Because, first of all, I can't just use this and let lambda bar be mu Z0 bar, because this F doesn't have the singularity that I need. But what can I do? Why don't I use a linear combination of the two? In other words, because remember, we've got a linear problem here. We just superpose solutions. So what I'm going to do is that one gives me the singularity of F that I need. And then I'm going to add this one in. And by the way, I'm going to keep this in. You'll see why. The point is, I want to add a second order pole at there, but maybe I'll need a bit of the first order pole. We'll see. Can't do any harm, because if it's not there, delta will be 0. Does everyone understand? Where lambda delta are to be found. This has the right singularity at Z0. This is lower and upper analytic, so it's fine. Okay, so this works. This works for all delta and lambda. Let's just work out what the conjugate is. And the derivative. And then we substitute. I'll do a bunch of calculations for you all at once. All I've done is I've substituted those two things into there and rearranged. So check this. So you should be able to see now what delta and lambda are. I have to pick them to be such that G prime looks like that. There's some upper analytic G hat prime. So clearly, this needs to be 0. And if that's true, that vanishes, and in fact that vanishes. And this thing on the top needs to be mu Z0 bar. And that, so lambda bar, because look, that needs to be that, plus mu Z0 must be mu Z0 bar. And that gives me lambda. Remember, I know mu. Everybody following me? It's the same as I did earlier, just a little bit more complicated because it's a Strassler near wall, not a Rotlet. So with lambda given by this and delta given by this, remember I know mu and I know Z0. So these are both given now. These are determined. Then I found the solution for a stresslet near a wall. Remember, my swimmer was also a stresslet plus a source quadrupole. So I'll leave this as an exercise for you. You need to work out what the F and G are for a source quadrupole near a wall. And that will give you some other things to add to F and G. the way, I hope you can see there's some non-trivial mathematics going on here. These all have to be the right numbers. By the way, another interesting thing is to ask yourself what the image distribution is. So similarly, find f and g prime for a source quadrupole. Near a wall, i.e., remember you want fz analytic and g prime looks like 2 mu epsilon squared over z minus z naught cubed. Near z naught. Okay, that's the source quadrupole. Just another exercise. Okay? And then you will have found, if you add those up, see, if you do this, I've already done it for a stresslet, in other words, this bit. If I do the same thing for the source quadrupole, and then add the two answers together, then I'll have found these, what I've done here is I've Taylor expanded the bits that are analytic at z naught. Okay, these, I've been calling these f hat and g hat prime, but I've just Taylor expanded them because they're analytic there. But you see, these are the f and g that satisfy the no-slip condition on the wall and give me the right singularity corresponding to the swimmer. Everybody with me? So this is great, because now I've put my little point swimmer near a wall and I know what the flow is. So I know what flow it generates that satisfies the no-slip condition on the wall. What I have to do now is determine how it moves. It's the only thing left. But that's quite easy because, of course, this is the singularity. What these swimmers do is they move with the regular part of the velocity field. That's why I've Taylor expanded. Okay, so this is the regular part of f and g. So what I do is I look at the regular part, so the ODEs, for the point singularity, i.e. the swimmer, are dz naught by dt. So here's your dynamical system now. We had to do quite a lot of work to get the dynamical system, but here it is. It's minus f naught, that coefficient, plus z naught times f1 bar, which is the second coefficient, plus g naught bar. Remember, this looks like minus f plus z f prime bar plus g prime bar, except I've just evaluated it at one point now, and only the non-singular part. And the other thing is rotate with basically twice the local vorticity. Okay, because there's always that factor of 2 between the vorticity. So in other words, what am I trying to say? You know, the vorticity is related to twice the angular velocity. Okay, and remember, P minus I vorticity is 4F prime. So you can kind of see, look, that this is P minus 2I omega is 4F prime. So you can see that if I want omega S is d theta by dt, that's how the angle of the swimmer changes, is minus the imaginary part of 2F1. F1, of course, being the non-singular part of the F prime. And it becomes a 2 because there's a 2 here. This is it. So it's 3 by 3 real time evolving thing, the x and y position and the orientation. And I'll write it down for you. It's this. Here it is. This is what we've been doing all this work to get. The nice thing is, it's an explicit dynamical system, non-linear, with a parameter. Okay, look how non-linear it is. Mu depends exponentially on theta, and it appears here and here and here. And then theta appears explicitly just there as the theta dot. At the same time, z naught is also an unknown. X naught plus iy naught, and z appears there, there, and there. Notice, by the way, that x naught does not appear in the dynamical system. In other words, the x position along the wall does not appear in the system on the right-hand side. Is that to be expected? Yes, because you don't expect the dynamics to depend upon whether it's happening here or here, because the wall's translationally invariant. So you wouldn't expect the right-hand side here to depend upon x naught. Okay? I mean, the swimmer is going to do the same thing over here as it would over there, if this is the wall. Is everybody? I feel like I've done lots of kind of algebra behind the scenes here, but ultimately, I'm only doing two things. I'm replacing the treadmilling swimmer by its effective point singularity description, and then I'm putting that singularity near a wall and using these analytic continuation techniques I was telling you to get what the F and G are. Then I've worked out what the velocity of the swimmer has to be. By the way, it's actually more convenient if I write it out in terms of here we go. X and Y. Here we go. So these are the equations for this point singularity near a wall. So can it move, can it translate steadily along the wall? Because remember these orbits we saw where it settled down to a steadily translating orbit. We saw that in the experiments, the numerical experiments. Do we have this behavior in this system? In other words, this steadily translation along the wall at constant speed. Well, in order for that to be true, we want it to be in constant orientation at a constant height, which means that dy by dt is 0 and d theta by dt is 0. Is there any possibility of that happening? Well, let's look at this. dy by dt is 0, certainly if cos 2 theta is 0. Okay? So in other words, if 2 theta is pi by 2, which is theta is pi by 4, okay? Which means that the swimmer is basically oriented like that, pi by 4. Then this is 0, and then can I make this also 0? Well, sine 2 theta isn't 0, but can I make this 0? Yes, I can if I choose y squared to be 3 over 2. Or in other words, if I have it at 45 degrees and then I have it at root 3 over 2 epsilon. Then this is 0 and this is 0, and this will be whatever it says it will be, but that's just the speed. So this is great, because remember, this swimmer doesn't move if there's no wall. But what we've shown here is that this swimmer near a wall can propagate at steady velocity at whatever the speed is. It's in the paper. So that was a good thing. So my artificial swimmer can propagate steadily. Now, I don't know if you remember from my slides. I don't want to get the slides up again. But when I was showing you these spheres and rods moving near a wall, they did these nonlinear periodic orbits. Do you remember that? And Yizar, in his paper, plotted a phase portrait with height above the wall against theta. And what he found was there was a steadily translating state. In other words, when it just moved like that. And then around it, he found orbits like this. Remember, which I called nonlinear periodic orbits. Okay, and basically they correspond to these things. Things getting closer to the wall, reorienting, and then moving away again. So what happened historically was I did all this mathematics. And actually, I didn't put it in this form. I did all the mathematics and left Yizar to work out what the dynamics is. And he was so excited when he plotted the phase portraits of this system and got exactly this. I didn't believe him when he told me because he was the one who basically, well, first of all, he rewrote it like this, which is obviously a lot nicer. And then he plotted the y theta phase portrait, and you get exactly what he saw, his spheres and his rods. Which I think is quite remarkable, because his spheres and his rods, completely different swimmer. I've got a circular treadmiller with a treadmilling action, doesn't change shape. So it's a completely different actuation, but qualitatively the dynamics is exactly the same. Roger, you look like you've got a question.
No.
All right. What does that tell you? By the way, people don't even know this because we never put this in the paper. But remember I told you that the sperm and the rods, they did this oscillation down to the steadily translating state. And what I've shown you here is that we get the steadily translating state here. But do you remember earlier on, we set U, capital U, to be 0. So the little c was 0. And I did that because I wanted it to be not move if there was no wall. But I can do all the same analysis by keeping c not 0, which means it would be a self-propelling swimmer near a wall. And guess what you get? This is in my student's thesis, but we never published it as a paper. If you keep U is non-zero, you get precisely that. So in other words, it kind of settles down to the steadily translating state. So for some reason, keeping the capital U in, so make it self-propelling, makes it almost like a dissipative thing. But you don't see it if it's not self-propelling. Okay? But yeah, you get these orbits. So we just get the steadily translating states, which are here, and if you perturb them, you get these. But as soon as you let it become self-propelling, you get precisely these. Now, I think this is fascinating. Because for me, what it says is...
Does that mean that it changes the stability of this?
Oh, that's another question. That's another question. By the way, it's very easy to see from the... You can do the linear stability analysis of this. It's explicit, trivial. These steadily translating states here are linearly stable. But then you just expect so, because look, if you perturb it, it just goes to one of these slightly oscillating orbits.
My question is, when will you include the C? No,
Oh.
C.
Oh, yeah.
So that means what you
Yes, it changes things, yes. But it still remains stable. Remember, we didn't study this in too much detail. You see, Yizar didn't believe me that if you kept the self-propulsion in, it would change to this. He didn't believe me. But I got my student to do it, and you get precisely this. So I think this is fascinating because people have been... Now, this is a provocative statement. But you see, I actually had to work all of this out from the scratch because people didn't even... The F and G that I've shown you now, you don't find them in the textbooks. I had to derive them all myself because I'd never used them before. But my point is, a lot of the dynamics that people spend a lot of computational effort trying to resolve using complicated boundary integral methods and all kinds of, even finite element methods some people use, you can study the dynamics a lot more simply with these model systems, and qualitatively everything's the same. By the way, I just noticed, next month I'm going to the American Physical Society DFD meeting, and one of the papers that's won a prize this year is by Eric Lauger and a student, I think. And what they do is they study these swimmers now with near surfaces of different types. And, of course, actually what they did is they did exactly the same thing I'm doing here. And they approximate a swimmer as a point singularity. But they'd done all their analysis in 3 dimensions using Fourier transforms. But nevertheless, the spirit of their paper is exactly what we've done here. And by the way, remember, this is the no-slip condition. But it would be very simple, for example, and I've never done it, but just think how simple this would be, to impose, for example, a Navier slip condition. That just means that the relationship between F and G on the boundary now will be slightly different. And in fact, that was one of the things they looked at in the paper. They looked at how the dynamics changes as a function of the Navier slip coefficient. And they did some other things as well. I think they put it near a free surface. But again, that would just change the nature of the... For a two-dimensional model, it's trivial changes. And you'd just change what appears in these ODEs. Okay, that's all I'm going to say today. If you've got any questions, let me know. But on the last lecture, I'm going to show you some other things. You see, it was a little bit embarrassing, but not really. Remember option 2 to solve this problem was to put the actual treadmiller near the wall. And I realized about a year after I'd written the paper that you can solve that in closed form with no approximations. And I'm going to show you how to do that because that uses some nice mathematics that occurs a lot, the reciprocal theorem of Stokes flows. Okay. So I'll show you that on Friday. Okay, good. Thanks for listening. It's a long day.